Alright, so look, this right here is a first order differential equation, right? And then we also know that for the first order differential equation, lag systems, the transfer function has a particular general format, right? Which is of this form. You have this, and then plus this is s, right? Plus 1, right? Let's write the s big, right? Yeah, so this is the general form, okay? But then we also know that this g is the same as the, what do you call it, the output Laplace transform, Laplace domain function, and then the input Laplace domain function, right? But then one thing you have to notice that we actually get this one from the original differential equation, right? This we actually get it from the original differential equation, right? Fine. So when you look at this equation up here, what you see is that we have 5 and times y the t, right? But then the actual thing is that the y that we are seeing there is actually the output, right? So in actual sense, it's in time domain, right? Which we can write this form. Let's use a different color, which we can write in this form, right? This, and then the u will be the input, which in this case we will call the forcing function, right? The change that we are affecting the system, right? So that will mean that there is a way that after we do the Laplace transform, we can end up getting the y, this here. We can end up getting this y on s and then u on s, right? But then when we started, we said something about them that for the first order differential equations, if you rearrange it in a particular form, you'll be able to find that kp easily, be able to find the time constant easily, right? We said that when you can rearrange it in a particular way, right? Which is this here. Talk about this. So we are going to apply it here, and then we actually do the Laplace transform as well, and then see if we are in the same place, right? So let's see. So without even doing the Laplace transform, let's see if we can rearrange it, right, to fit the format that we discussed earlier. So that'll be 5 on 2, right, and we have dy dt, right, plus y, and then we have equal to 8 on what 2, and then u, right, 8 on 2, which is this will be 2.5, and then we have dy dt plus y, and this will be equal to 4u. And we said if we have it in this form, we'll clearly know the kp. So the transfer function should be of this form, which will be the kp, the gain, which is per what we said, will be this here, 4, right? And then the time constant will be this, right? So this is the time constant, and this will be the gain, right? So if we bring this to the format that we are talking about, which is this way, right, we will get the gain is what, 4, so that's 4, and the time constant is 2.5, right? Time constant is 2.5, and then s, and then plus 1, right? So clearly, even without even doing the Laplace transform, we get this form, right, per what we discussed. Now we are going to do it step by step, going through the actual Laplace transform to see if we get the same thing, right? If we get the same thing, and we are supposed to, we have to, if we actually follow the procedures, right? So now let's see. And then before we do that, now when we look at this equation, we can see something about it, right? So before that, let's do the Laplace transform first, right? But let's see, we know that the input is just one, right? The input is u, the output is y. So right, so what we can say about this system is this process is that it's a single input, single output, and we said that we have different types. We can have a single input, multiple output, right? We can also have a multiple input, multiple output, and we can have a multiple input, single output, right? We've said about all these, right? And then the system that we're having here is single input, single output, right? You can clearly see that because of that, you have just one transfer function, right? That would mean that systems of this way, right, will have different transfer functions. The transfer function won't be just one. So multiple input, multiple output, that the transfer function won't be just one, it'll be multiple, right? Fine. So let's finish up with this. Okay, let's see. So if we are doing the Laplace transform, and then we are assuming that all the initial conditions are equal to 0, clearly we will get 5. This is just an assumption, it's not the case all the time, right? So this means that we'll get 5, and then we'll have s, and we'll have what, uh, right? And then we already know that we've discussed this, that when we said that when we have a function like this and we do the Laplace transform, it becomes something like this, right? So we move from y of t to y of s, and because we have when we have u of t, we also change to capital U of s. We've said this already, right? Fine. So now that we have this, it means that, and we know that the transfer function, we know the transfer function, we know that the transfer function is the ratio of the output transform on the input transform. That would mean that we have a way to rearrange all this to get the transform that we are looking, the transfer function we are looking for, right? When it comes to first order differential equation lag, right? First order lag processes, the transfer function is of this form, where we have the gain, right? And then we have the time constant is plus 1. This one here is very important. So that will mean that we have to make sure this here is 1, right? So in order for us to do that, let's see. In order for us to do that, what we do is that we divide the numerator and denominator by 2. That gives us 4 on what, 2.5 s plus what, 1, which is the same as what we had here, right? So this here, which is the final, this one, right? 4 on 2.5 s plus 1 is the same as 4 2.5 s plus 1. So clearly, if you rearrange it that way, to works, right? That's for first order. Right? We've not done how to do the same for the other one, so but that's for first order. It works even without you doing the Laplace transform. And then this is assuming that this is clear. This is assuming that if you do it this straightforward this way, right? It's assuming that all the initial conditions are 1, right? Because that's how it works. Because here we assume all the initial conditions. Sorry, we are assuming that all the initial conditions are 0, right? So the same thing applies here. That's why when we went through the process, all the initial conditions were 0. That's why we are having this, right? So this is it. So fine. So here we clearly know that this system or this process here is a single input, single output, right? Okay. So here this is the same as d of s, the transfer function, right? So basically, now let's talk more about the transfer function, right? We said is the y of s, the output, right, all over what, the u of s, the input, Laplace transform. That will mean that if you want to find the output function, the Laplace transform of it, if you have the transfer function, right, you can multiply it by the u of s in Laplace transform, right? So this is what this one means, right? So is the this here is the output function in Laplace transform. This is the transfer function in Laplace transform. This is the input function in Laplace transform, right? Fine. And then we'll look at examples that actually require to understand these things, right, before we'll be able to continue. Fine. So that will mean that if you have a function or if you have a system where the input is more than 1, the output is more than 1, you have different transfer functions, right? So let's say you have a system where, so let's see, in the system you have input, right? And we know that the input, we can have a measure manipulated and disturbance. So if a system has a manipulated and a disturbance, and then let's see, has just one output, that would mean that you have a transfer function. So let's say just one output. That would mean that you have a transfer function that compares this an output. So let's say the output is, let's say, t. So that means you have one transfer function, right? As a result of the disturbance, right? Which is this a case study. What I think here is a case study. That means I have one transfer function that's relating the output. So let's make it y. Right? That's relating one output to the disturbance, right? And you have another transfer function in terms of the manipulated variable that's comparing the output and the effect that the manipulated variable has on it, right? So the more the variables that you have or the disturbance you have, all these things will affect the number of what's the name? The number of the transfer functions that you will get, right? The number of transfer functions that you get. Fine. Yeah. So now that we have these basics in mind, we are just going to try a few more examples, right? So let's see.